Have you ever wondered how many atoms are in a drop of water? Well, that question isn't as unanswerable as it might seem at first glance. The key to unlocking this riddle lies in a fascinating concept in chemistry known as a mole. Now, before you start picturing a small, burrowing mammal, let me clarify, in the realm of chemistry, a mole is a unit of measurement. But what does a mole measure? It quantifies the amount of a substance, but not in grams or liters or any other units you might be familiar with. Instead, a mole measures the number of entities like atoms or molecules in a substance. It's a bit like a dozen, which always represents 12 of something, except that a mole represents a much, much larger number, nearly unimaginable in its vastness. This is where Avogadro's number enters the picture. Named after the Italian scientist Amedeo Avogadro, this number, approximately 6.022 times 10 to the 23rd power, is the number of entities in one mole. So why is the mole concept so essential? Well, it allows us to deal with the minuscule atoms and molecules that make up the world around us in manageable and understandable quantities. It's a bridge between the atomic world and the macroscopic world we can see and touch. Take our initial question about the drop of water. By using the concept of a mole, we can determine the number of water molecules in that drop. We can't physically count each molecule, they're far too small and numerous. But with the power of a mole, we can use Avogadro's number to make a pretty accurate estimate. This is the magic of the mole concept. It allows us to quantify the unquantifiable, to make sense of numbers so large they boggle the mind. Whether it's understanding the composition of a star light years away or simply knowing how many sugar molecules are in your morning cup of coffee, the mole concept is an indispensable tool in the toolbox of science. So with the power of a mole, we can count the uncountable. Now, what exactly is a mole in the world of chemistry? When we think of a mole, a small burrowing mammal might come to mind. But in the realm of chemistry, a mole takes on a whole new meaning. It's not a creature, but a unit of measurement. Just like a dozen represents 12 of something, a mole represents a much, much larger number of particles. Let me introduce you to a term that's as fascinating as it sounds: Avogadro's number. Named after the Italian scientist Amedeo Avogadro, this number is a whopping 6.02 times 10 to the power of 23. That's a 6 with 23 zeros trailing behind. Imagine trying to count that high. But why such a ginormous number, you ask? Well, the universe operates on a scale that's hard for us to comprehend. Atoms and molecules, the building blocks of matter, are incredibly tiny, and it takes an astronomical amount of them to make up anything noticeable. So, when we say a mole of any substance, we mean that it contains Avogadro's number of particles. This could be atoms, molecules, electrons, or even donuts if you're feeling peckish. This gives the mole a special role in chemistry. It's the bridge that allows us to walk from the world of atoms, which we can't see or touch, to the tangible macroscopic world we navigate every day. For instance, 1 mole of carbon atoms weighs about 12 grams, which is something we can measure on a scale. But that same mole also tells us there are roughly 6.02 times 10 to the power of 23 carbon atoms in those 12 grams. Isn't it fascinating how the mole concept connects the atomic scale to our everyday life? It's like having a translator that speaks both Atomese and human. And that, my friends, is the magic of the mole in chemistry. In other words, a mole is the bridge between the atomic world and the macroscopic world we live in. So, how do we calculate the number of moles in a substance? That's the big question we're going to tackle right now. It's simpler than you might think, thanks to a handy formula. The formula to calculate the number of moles is moles equals mass divided by molar mass. That's right, you just need to know the mass of your substance and its molar mass, then do a little division and voila, you've got your answer. But wait, you might ask, what's this molar mass you're talking about? Well, I'm glad you asked. Molar mass is a critical concept in chemistry. Simply put, it's the mass of 1 mole of a substance. And where can you find this elusive molar mass? Right on your periodic table. Each element on the periodic table has a molar mass, which is typically listed under the element's symbol. For instance, let's look at carbon. Carbon's molar mass is 12.01 grams per mole. This means that 1 mole of carbon has a mass of 12.01 grams. So if you had a sample of carbon that weighed 12.01 grams, you'd know you had exactly 1 mole of carbon atoms. This formula becomes your best friend when it comes to mole calculations. It's your ticket to understanding so much more about the substances you'll encounter in chemistry. So, don't be afraid to get cozy with it. Practice using the formula with different elements and masses until you feel comfortable. Like any good friend, the more time you spend with it, the better you'll understand it. And trust me, this is one friend you'll want to keep around. It's going to help you unlock so many doors in your journey through the world of chemistry. Remember, the key to mole calculations is knowing your molar mass. Get that down, and you're well on your way to mastering mole calculations. So grab that periodic table, find those molar masses, and start calculating. Now, let's put our mole calculations to the test. Imagine you're a scientist and you're given a task to determine the number of moles in a certain mass of water. Let's say you have 100 grams of water. How many moles of water are in that sample? To answer that, we need to remember Avogadro's number, which is roughly 6.02 times 10 to the 23rd power. This number represents a mole, and it's the number of particles in a substance. But how do we apply this to our water sample? First, we need to figure out the molar mass of water. We know that a water molecule, H2O, is made up of 2 hydrogen atoms and 1 oxygen atom. The atomic mass of hydrogen is approximately 1, and oxygen is about 16. So if we add up the atomic masses of the atoms in a water molecule, we get around 18 grams per mole. Now we can use this information to calculate the number of moles. We take the mass of our sample, 100 grams, and divide it by the molar mass of water, which is 18 grams per mole. The grams cancel out and we're left with the number of moles. So 100 divided by 18 is approximately 5.56. That means there are about 5.56 moles of water in our 100-gram sample. The beauty of mole calculations is that they allow us to bridge the gap between the macroscopic world we can see and touch and the microscopic world of atoms and molecules. By understanding the mole concept and how to perform these calculations, we can gain a deeper understanding of the world around us and the invisible world within every substance. And there you have it, the number of moles in our sample of water. So, what have we learned about mole calculations today? Well, we've covered a fair bit of ground, haven't we? From the very definition of a mole, to the significance of Avogadro's number, to how we actually calculate moles and apply these calculations. Let's take a minute to distill these points. Firstly, we dove into what a mole is. It's not a small creature burrowing through your garden, but rather a unit in chemistry that measures amount of substance. It's a bridge between the macroscopic world we live in and the microscopic world of atoms and molecules. We then learned about the importance of Avogadro's number. This colossal figure, 6.02 times 10 to the power of 23, is the number of particles in 1 mole of any substance. It's a fundamental constant in chemistry and a cornerstone of the mole concept. Next, we tackled how to calculate moles. Remember, it's not as scary as it sounds. All you need to do is divide the given mass of the substance by its molar mass. A simple division, but a crucial tool in the toolbox of every budding chemist. And finally, we looked at the real-world application of mole calculations. Whether it's determining the amount of reactants for a chemical reaction or figuring out the composition of a compound, mole calculations are an indispensable part of our understanding of chemistry. So, in essence, mole calculations are the linchpin that connects the visible and invisible worlds, allowing us to quantify and manipulate the unseen. It's a concept that might seem daunting at first, but once you've got a firm grasp on it, you'll find it's as natural as breathing. In conclusion, understanding mole calculations not only helps us grasp the microscopic world of atoms and molecules, but it also opens up a world of possibilities in chemistry and beyond.